So here is a sodium chloride lattice. It's a soluble salt, but it's important to recognize if no water is added, then it remains like this. This is a grain of salt. In reality, within the grain of salt, the ions will be wiggling a little bit, so this is realistic. If I want to dissolve this grain of salt, need to add water. The amount of water you add is important. If you don't add enough water, it can't dissolve the entire grain of salt. So here I'm adding a couple waters, and you can see the water does separate the ions, but they always have a tendency to come back together. So if there isn't enough water molecules, then there will be some solid, and that's called saturation. So you've seen this when you made your density bottles. If you added too much salt, not enough water, then you had solid salt that could not dissolve. So you need enough water molecules to separate all the ions, and then you'll say the salt is dissolved. I like to say when the salt is dissolved, the bond is dissolved. That's true for ionic substances. Now let's talk about some weaknesses of this model. You see there's a lot of emptiness. And empty space should remind you of the gas phase. And this is supposed to be solution phase. So the reality is that it should be really packed with water. And I can't do it to the extent that it should be done, but if you imagine maybe for each ion, for each green or orange ion, there are 6 to 10 water molecules, that would be a more realistic representation of the spacing. The other thing that's not being well modeled here is the idea that the water molecules are attracted to these ions. Right now they're just bouncing off. But in reality, there would be interactions, attractions between water molecules and the ions. I would need to change the model to show that well. So what's good about this model is the idea that it's very fluid. Clearly the ions are swimming about. And that's true. When you have a solution of a soluble salt, a salt dissolved in water, everything's quite fluid. So now I'm going to use the power of reversing time to talk about what happens if we start evaporating the water. If you start boiling it. You've done this in the lab. So now I'm running it backwards in time. And as you heat it up, the water molecules will move faster, and they'll get to the point where they can vaporize. So in this simulation, you'll start seeing them disappear, and you have to imagine that that means they have evaporated, boiled them away. So here they go. You're starting to see fewer and fewer water molecules as they evaporate. And what that means is that it's much more likely for the ions, the orange and the green ions, to bond together. As the number of water molecules diminishes, there's less chance that they will be separated. So you're starting to see clusters here. As the water molecules diminish in number, the ions will cluster together, and when you evaporate all the water, then we'll be left with that nice crystalline salt crystals at the bottom of the dish that you have seen when you evaporated the water out of a salt solution. There they go. The last of the waters are evaporating. And you can see the salt crystals are reforming here. If there's nothing to separate them, their natural attractions will bring them together. the last water molecule will evaporate, and we're left with a crystal of salt. So the reason the salt itself can't evaporate is because there are strong attractions keeping these ions in their places. So you can see if I try to drag this away, snap, it goes right back. So this ion is pulled by the negative ions here, so it goes back to its place. And these strong attractions make it so that this ion really can't ever escape, snap, right back where it came from. So that's why you're left with the salt in the bottom of the dish after the water molecules, which are more free, which are less bound, the water molecules can evaporate. These salt ions cannot.